Let's look at an example of how you can model an exponential model from data. The first thing you do is you put the data into your calculator. We have our x values and our y values. I've already entered them into the calculator. And then I set up a scatter plot on my stat plot screen. It's a scatter plot using the data in list 1 and list 2. And if I graph that, you see the scatter plot that we get. And the problem with this scatter plot is that it's not straight. It's got some curvature to it, and because of that we can't fit a straight line to the data. If we were to do that, then our predictions in the middle of the data values would be too high, and our predictions at the ends on the right or on the left would be too low. So we're going to get some systematic error either way. So a linear model is not appropriate here. Okay. Now when you look at those data, you could ask yourself, is this growing according to some kind of a power law process or some sort of exponential process? One way to check if the data follow an exponential process is to look at ratios of successive y values. We can do this because the x values are evenly spaced. If the x values are not evenly spaced, you wouldn't want to try this test. But you can divide 7.6 by 5.3, and you get approximately 1.43 for that ratio. If you divide 11.0 by 7.6, you'll get approximately 1.45, which is pretty close to that. If you divide 16 by 11, you get approximately 1.45 again. 24.1 divided by 16.0 is about 1.51. 33.8 divided by 24.1 is about 1.40, and 43.4 divided by 33.8 is approximately 1.28. Now these ratios are not all exactly alike, but they're pretty close. And when you see that, if the ratios of successive y values are approximately the same, that indicates that there might be an exponential process underlying these y values. Now remember, this test only works when the x values are evenly spaced. If the x values are not evenly spaced, you can't do this. Okay? Now suppose that were the case and you can't do this test. What else could you do? Well, one thing you could do is to try to straighten your scatter plot by logging the y values and seeing what happens. So what we're going to do here is we're going to take the logs of the list 2, and we're going to store that in list 4. Now when I log the y's, I store them in list 4. When I log the x's, I store them in list 3. So we press enter, and our logs are generated and they're stored. And then we can go back to our scatter plot, and we can change the specification of the scatter plot so that we're using list 4 instead of list 2 for our y values. And then if we zoom 9, we get a straighter scatter plot, fairly linear, except for this little one at the end that's a little bit small relative to the trend of the others. But this is a much better candidate for a best fit line than the other scatter plot was. So now what we have to do is go stat calc 8, and then when we do this regression, we're going to put in list 1 for our x list. We're going to put in list 4 for our y list, and then we can store our output. If we go to vars, y-vars function y1, we can store this regression line in the y1 screen, and there you can see it. Okay, it's a linear model between the logs of the y values, of the original y values, and the unlogged original x values. And you can see that a is 0.73095, about 0.7310, and b is about 0.1563. R squared is 0.997, very high. Correlation is even higher, 0.9985. And these both indicate, well, this one, the R squared, indicates a very good fit between the log of the y values and the unlogged x's. And this R indicates a very strong positive linear association between the log of y and x. Okay? Now what we want to do is take this information from here and put it back into a form that is truly an exponential model. So what we'll do is we'll take the original regression equation, which is log of y with a hat on it, is approximately 0.7310 plus 0.1563 times x. Now what we want to do is transform that back into an exponential model. Now the way we do that is we want to get a model that looks like y hat equals capital A times capital B to the x. Now to get capital A, we're going to take 10 to that power right there. Should say approximately equal to 10 to the point 7310 power, and we get approximately for that about 5.3827, and for B, capital B, that's approximately equal to 10 to the 0.1563 power, and that's approximately equal to 1.4332. So our exponential model looks like this. Y hat is approximately equal to 5.3827 plus, or times rather, 1.4332 to the x power. And that's our exponential model, and that's the model that we should use when we're trying to make predictions. Okay? If, say, x equals 8, then y hat would be approximately equal to 5.3827 times 1.4332 to the 8th power, and that's going to be approximately 95.8196, and that's our prediction for the value of y, predicted value of y when x is equal to 8.